So we come to the final lesson of chapter 2 in our book, and we're talking about parent functions and transformations. In a previous lesson, we talked about the parent function, which was the absolute value function. And, well, we'll talk about these as we go along. So we're going to identify and use parent functions. A parent function is just like the function before we do crazy stuff to it. So it's what the parents look like before the kids come along. Because, you know, every kid looks like a parent, but yet they've got their own variations. And so that's kind of what we're talking about with these this idea of parent functions. We'll also look at some transformations. But a family of graphs or a group of graphs that displays one or more similar characteristics, like lines or lines. You can see we have the quadratic function, which is a parabola. We have the constant function, which is linear. We have the identity function, which is also linear. But we have the absolute value function, which is V-shaped, and so on. And we will see, you know, square root functions, exponential functions, and they all have certain characteristics that they share. And they may be thinner, they may be taller, they may be a variety of things, go up faster, go down slower, just many things that can happen. Sometimes they're reflected across the x-axis, and so you remember the parabolas, you know, the x squared is like this, but if the coefficient of the x squared is negative, then it went down. And so we probably remember that, we certainly should. But those are the things that we're talking about here. You can see the quadratic function, which you're familiar with. We'll do a ton of stuff with this coming up in chapter 5. So let's get started with this and just looking at some of these parent functions. The constant function we mentioned is really a horizontal line. It is a type of the linear, and it's just where f of x equal to a, where a is some constant, some number. The identity function, where y equal x, which, you know, 0, 0, 1, 1, 2, 2, 3, 3, negative 1, negative 1, negative 2, negative 2. Y is equal to x is the identity function. It is what it is. Whatever x is, what y is. Whatever y is, what x is. The absolute value function that we talked about before, f of x equal to the absolute value of x, you can see where it goes. But remember, we looked at where, in a previous lesson, where it moved a little bit. You know, it can move up, it can move down, it can move left, right, and then the quadratic, which we're familiar with. Now, this is the parent, but later, we're going to begin to look at these functions, these quadratic functions, in this form. This is a special form, and it will allow us, this HK business is going to become super, super familiar. So those people who've already had geometry saw HK as the center of a circle. Probably remember that, you should. And so this HK is going to show up all over the place. We're going to deal with it in here and in a variety of other functions, because the HK is going to help us understand the transformation. You also see the A, and as we mentioned before, if it's positive, it opens up. If A was negative, it opens down. And so this is the parent, this is what the parent looks like. This is like normal, and then the kids come along and the crazy starts. So identify the type of function represented by the graph. It's V-shaped, so it is absolute value. It's not the parent, because the parent comes down to 0, 0, but it is in that family. Identify the type of function represented by the graph. Well, it's parabola, so it's quadratic. It's not the parent, because it comes down to 0, 0 at the vertex, but it is quadratic in nature, and so that's the type. This one, it's horizontal line, y equal 2. It is the constant function because it never changes. Y is 2, y is 2, y is 2. Doesn't matter if x is positive, negative, fraction, decimal, it just doesn't matter. It's y is 2, y is constant, answer is B. It's a constant function. That one should be pretty easy for us because we did it just a few minutes ago. 0, 0, 1, 1, 2, 2, negative 3, negative 3. It is the identity function, y equal x. Identity function. So it says, describe the translation in this, then graph the function. Describe the translation, then graph the function. It's hard to kind of even know where to start with this because there's so much cuteness in this problem. Problem says y equal the quantity x plus 1 squared. So I'm going to go back and right here remind you of what we did or what we said a few minutes ago about h and k. Now, in this particular problem, h is -1. Look at this form, look at this, h is -1. Because it's always opposite sign of what you got because of the subtraction in this form. So h is -1. K is 0. So instead of the vertex coming down like, let's do it this way. Instead of it coming down and hitting the 0, 0 like is the parent, the kid is going to come down and hit -1, 0. The child is going to be like that. And really what that is the parent just scooted over one place to the left. Now, we could have done this a little differently, a lot differently, and we could have used T-chart. I'm not going to do too many, but I will do a couple. -2, -1, 0, and 1. Let's just do those. So -2 plus 1 is -1, squared is 1. -1 plus 1 is 0. 0 plus 1 is 1, squared is 1. 1 plus 1 is 2, squared is 4. So you can see, if we graph that, -2, 1, -1, 0, 0, 1, and 1, 4. Something like that. So you can see the graph. If you hadn't have known the HK, or if you, well, you didn't know, but if I hadn't shown you the HK, we could have graphed it anyway. Certainly with the calculator we could have graphed it. We could have graphed it with a T-chart. So describe the translation. It shifted one place to the left. Nothing happened to it as far as it didn't get any bigger, any narrower. It just shifted one place to the left. That's what it did. So it's just the parent scooted over. So describe the translation in this. So thinking about this the same way, the parent, of course, that's an absolute value function, so the parent looks like this. And this, if you look at y equal a times the absolute value of x minus h plus k, throwing that hk in there, you can see the h is 4, hopefully, and the k is 0. So at 4, 0, that's where that's going to come down to. It's going to look like that. So what does it do? It takes and scoots this over 4 places or 4 units to the right. Answer is C. And you can see the parent and the kid. Now we could have done that with the T-chart. I didn't bother to walk you through the T-chart on that one, but we could have proven it by the T-chart, not just have to rely on the HK. But the HK is great, and you're going to do a lot of stuff with it. So let's talk about the HK. So in this problem, what's H? 3. And what's K? 1. So here's the parent. So we're going to move over 3 and up 1. Because that's what H and K are when you look at this form. Okay? In this one, what's the H? -2. Remember, it's all the opposite sign. What's the K? -1. It's not the opposite sign because it's a plus K. So whatever it is what it is. That, then, if you take this graph, this is the parent, the vertex is going to move to -2, -1. Now, if we want to take a time, let's put in 1, 2, 3. Let's put in -4 and see if we get 1. Put in -4. -4 plus 2, -2. Absolute value of -2 is 2. 2 minus 1 is 1. It worked, right? We said -4, 1. Let's put in -2, which is supposed to give us -1, right? Put in -2 and see if we really get that. Put in -2. Put in -2, you get 0. Absolute value of 0 is 0. 0 minus 1, -1. It works. And we could go on with these. I probably won't graph them all, but I'll just go through the HKs with you so that you can see it. So what's the H here? Remember, it's that H minus H plus K. So the H is 3, the K is a -4. Here, the H is 0, the K is 3. HK. Got to be able to do that. You got to be able to do that. You got to be able to do it. Similarly with the quadratics, the parabolas, we have the HK business, and the H and the K are going to tell us what happens to the vertex. You go left, right, up, down. How's it going to work? Here's the parent. Here's the form for looking at the children and how they're being transformed. So our H here is 3, and our K is 1. So let's draw the parent, and this is a so-so, not exact. So it would be over 3 up 1. That's what we think it would look like. Over 3 up 1. We could put some numbers in and see if they are anywhere near correct. Like we could put in 1, 2, 3, 4. We could put in 4. 4 minus 1 is 4 minus 4. Give it away. 4 minus 3 is 1. 1 squared is 1. And 1 plus 1 is 2. So it'd be 4, 2. And you can see I'm pretty close there. My graph's not perfect. I knew it wasn't before it started. This one, the H is at 2, and the K is -3. So that would suggest that the parent function gets moved over 2 places to the right and down 3. Well, first of all, if I put 2 in, I should get -3, and I do. But let me put in something else like 0 and see how close we are to something here. So put in 0. What is 0 minus 2? -2. What's -2 squared? 4. What's 4 minus 3? 1. So 0, 1. You can see I'm off just a little with my graph. But I knew I was. I could tell. But it's still in the neighborhood. And for right now, that's good. So let's continue. What's the H here? Oops. What's the H here? -4. What's the K? -1. Remember, it's the opposite sign here because the original form is X minus. So that'd be like a double -4. That's why it's a -4. And then the -1 for the K. So we could easily graph that. Let's just finish up with this. The H is -1. The K is 0 because there's no number out here. But identifying the HK is really, really easy for us to do. So describe the reflection in this one. So remember the parent, V-shaped, absolute value. But because the A is negative, what's going to happen? That's going to be flipped down. So you're going to end up with something that looks like that. And you could try that really quickly. Let's just plot a couple of points. -2, 0, and 2. So if you put -2 in here, the absolute value of -2 is 2, but you got it's -2. Put the 0 in here, it's 0. Put the 2 in here, absolute value of 2 is 2, but it's -2. So where are those points? -2, -2, 0, 0, and 2, -2. So you can see it just reflects across the y-axis. That's what they say, that's what they got. That's how that works. They put the parent, they put the kid. Describe the reflection of this. Well, we learned this in Algebra 1, that if the A is positive, it opens up. If A is negative, it opens down. So basically, it's going to do the reflection across the y-axis or the x-axis, and so that is going to be A. parent, kid, right? Fold the paper, there you got it. So describe the dilation. Now, let me graph the parent first. And just gonna, pretty close. 1, 1, 2, 2, 3, 3, so on. But if we do this one, and let's just do, let's do all the positives for a second. Let's not do that. Hold on. Let's do -4, -2, 0, 2, and 4. I said we do positives, I changed my mind. What's the absolute value of -4? 4. What's half of 4? 2. Absolute value of -2? 2. What's half of 2? 1. 0, 0, 2, 1, 4, 2. Take the time to plow through those and see. So, -4, 2, -2, 1, 0, 2, 1, 4, 2. And maybe remember with parabolas that when you have an a that is between 0 and 1, you remember when it was a parabola, you had a between 0 and 1, it compressed it, pushed it down. And that's what happens here. In other words, y is going to go up half as fast as it did in the original parent function. And so you can see that's what happens. It pushes it down, right? And so that's describing the dilation. It compresses it. So there's the parent, there's the kid. It goes up slower, half as fast. You can get stretched or compressed. Those are our options. So we look at this one. We know what the parent does. V shape. You know what the parent looks like. And we can look at the kid, like 0, 0's, it's still a point. -2 would be 4, right? Well, it's probably up there. And +2 would be 4. And so you can see what happens is it goes up a lot faster. The 2 pushes it up a lot faster. So what does that say? The dilation of the graph is stretched vertically. It didn't get translated. The vertex is still where it was, but it is stretched vertically. The function blah, 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 blah can be used to represent a parabolic archway. Describe the transformations in the function, then graph the function. Let's talk about the HK. H is 5, K is 12.5. So translations, or transformations, is 5 places to the right and 12.5 places up. Right, from wherever normal is, like it's a parabola, wherever normal is the vertex going to go over 5 and up 12.5. So something like that. But because this is negative, it's going to flip down. So it's going to open down. And because this is in between 0 and 1, it's going to be flatter, right? Instead of it'd be like compressed, except it's upside down, so it's compressed. So those are the things that we can see. So you can see, here's the parent, there's the movement that it gets, and it's compressed so it doesn't go as steep as the parent, it's a little flatter. And that's supposed to be, didn't show it, that's supposed to be an archway. Which the following is not an accurate description of the transformations in the function. So just for us, we know it moves 4 places to the left because H is -4. Moves 2 places down because K is -2. It reflects across the x-axis and it's going to be compressed. So you can see this says it translates 4 units to the right, which is wrong. Move 4 units to the left. In fact, when you look at these two, it can't do both at the same time. Hint, hint. And so the one that is not accurate is A. Now, it did do the other things, and we mentioned that. 2 places down, we said that's what was gonna happen, and it's reflected, so we said that was gonna happen, we said that was gonna happen. So, we just have these pictures. And I could say that in your Algebra 2 here, and in the future in your pre-calculus and calculus, I remember when I took pre-calculus, I felt like I was a member of the National Graph Society. Like, we graphed all the time. But it wasn't always graphing like plotting points like a T-chart. I couldn't tell you how many instructions I saw that said, sketch the graph, sketch the graph, sketch the graph. Well, sketch the graph means give it a pretty good look of how it would be. It doesn't have to be exact, precise. You don't have to plot every 1, 2, 3, -1, -2. You're just getting an idea of what the graph is going to look like. Sketch the graph. It's not perfect. It's not exact. It's just a sketch. And in doing that, we can look at these things and we can see how they affect things. So we've already dealt with it, but if you have x plus h, then it moves it to the left because it's opposite. Remember, it's opposite. So it'd be like a negative, whatever that number would be. So it moves it to the left. That, the h will be positive, so it moves it to the right. Here, where the k, remember it's outside, k, if it's positive, it goes up. If it's negative, it goes down. It's just like we'd expect. Here, it reflects it across the x-axis, which is normal when the a is negative. But when you put a negative inside and change the x, it reflects it across the y-axis. We don't deal with this in as much, but it's at least there for you to see. And then these can stretch it vertically or compress it vertically. We already know if it's bigger than 1, it stretches it. If it's between 0 and 1, we said a couple times already, it compresses it. And then we've got this, which is inside the function instead of outside the function. And that's the one we saw where we had the absolute value of 2x. That's more like this one. And you can see that it gets compressed and expanded horizontally as opposed to vertically. We'll see that, but it's not as big a deal.